Swayam Prabha. Digital India. Educated India.
Okay, good morning. So, we will be talking about distillation from this class onwards. So, distillation is a mass transfer operation that involves separating components of a liquid mixture, such that there is a two phase, gas and liquid, and all the components are present in all the phases. Okay, so this has to be contrasted with absorption, where one of the component, one of the solute was transferring from gas to liquid or vice versa. But in distillation, on the other hand, all components are present in both phases. Okay, so that's one characteristic difference. The second is, in distillation, the gas phase is created from the liquid itself by partial evaporation. Again, if you remember from absorption desorption problem, where a new phase, a gas phase or a liquid phase, was introduced so that the solute can have more solubility. Okay, for example, in absorption, you introduce a new liquid phase so that the solute can be transferred from gas to a liquid. Whereas in the desorption problem, you will actually have a new gas that is sent to a liquid mixture, so the solute can transfer. So, absorption desorption involves introduction of a new phase, but in distillation, that new phase is actually created within from the liquid phase itself by partial evaporation. Okay, so those are the characteristic differences. All components are distributed in both liquid and gas phases. Even though we say both components are distributed in both phases, but the distribution is unequal. One component is distributed more in gas than in the liquid. So, the distribution is unequal. Unequal distribution is the key. Third is, the gas phase is created from the liquid phase. By partial vaporization. So, these are the characteristic features of distillation in comparison to, let us say, absorption or desorption. Now, we also have to distinguish this term distillation from other similar processes such as evaporation. Okay. So, evaporation versus distillation. In evaporation, one of the component will be non-volatile. Okay. To give an example, if you take a aqueous salt solution and then you evaporate the solvent. So, here in the gas phase, only the solvent will be present. The solute, which is salt here, will not be present in the gas phase. Okay. So, such an operation we call it as an evaporation. Only solvent vaporizes. Solute is non-volatile. Okay. So, such a process we call it as an evaporation. Whereas distillation, on the other hand, as I said before, both components are volatile, both are evaporating to the gas phase. Okay. I have already mentioned about an example of a distillation in the introductory class, but again, suppose if you consider ammonia water solution, okay, ammonia plus water mixture. Okay, I am talking about liquid mixture at certain composition. So, let us say you do a partial vaporization. When you partially vaporize this liquid mixture, both ammonia as well as water will evaporate into the gas phase. Okay, but the gas phase will be rich in ammonia than water. This is what I meant as unequal distribution. Ammonia distributes in the gas phase much more than water. So if I take that gas, part of the gas which I vaporized, and then if I condense it into liquid again, okay, if I condense this distillate, I get a liquid mixture again as a combination of ammonia plus water. Okay, this is a liquid mixture. And the difference between this liquid mixture versus the initial original mixture is that in the distillate, the composition of ammonia will be more than that was in the original. So all we have done is we have taken the original solution, partially vaporized it, and then we collected the vapor, and then we condensed the vapor into a liquid again. So we basically start with the liquid, end with the liquid. However, by doing this partial evaporation and condensation, what we have achieved is we have enriched the solute, one of the solute in the distillation. Okay, so when you do the partial vaporization, you got gas, but there will be also some liquid present because you have done only partial vaporization. And if you look at the composition of that residue liquid, you will see that would be lean in ammonia but rich in water. Okay, so you start with one liquid solution, you partially vaporize it, you get two fractions. One is a gas phase, another one a liquid phase. The gas phase again you condense into a liquid form, and that would be rich in more volatile compound, in this case ammonia, and the residue would be richer in the non-volatile compound or less volatile compound, in this case water. So by simple one cycle of partial vaporization and condensation, you are able to achieve some level of separation. This success of separation depends on how much ammonia is more volatile than water. Okay, as long as this one of the components is more volatile than the other, the separation will be more and more effective. Okay, so if I take this particular distillate, and if I do one more cycle, I take this one, I vaporize it again partially, collect the distillate, and I look at the composition of ammonia, it will get richer than this solution. And you can think about repeating this over and over so as to get much more richer ammonia solution. But as you do this, you are only partially evaporating. So the actual amount of distillate that you are generating in each process will keep on diminishing. Okay, you are increasing the purity, but you are actually decreasing the actual number of volume. Okay, so that is the characteristic of a distillation. And suppose if you look at desorption versus distillation, desorption also involves a liquid mixture and purifying one of the components. So here we introduce a new gas phase so that the solute can transfer from liquid to the gas phase, and thereby you separate the mixture. And in this case, we have a choice of choosing the gas phase. This gas phase can be chosen based on variety of considerations. Which gas is more soluble for the solute, which is cheaper, what is easy to handle. So there are so many things you can use to choose this particular gas. Whereas in the distillation, you don't have such a choice because the gas has to be generated from the liquid mixture itself. So the chemical nature of the gas and the liquid are very similar. Whereas in the desorption case, gas can be completely a different chemical constituent compared to the liquid mixture. So that's something that you have to keep in mind. So as with any other mass transfer operation, understanding the vapor liquid equilibrium or the equilibrium line that I call is very important. Okay, when we dealt with the absorption and desorption, the equilibrium line was given by laws such as Henry's law, Raoult's law, etc. Okay, looking at how the composition of the solute in the gas phase versus liquid phase are related. Okay, in the same way, in distillation also, this vapor liquid equilibrium is very, very important concept, and that's a very basis of doing mass transfer calculations. Okay, so now let's say for the purpose of the discussion, we will think about a binary mixture. Okay, let's say you have solute. In this case, there is no solute solvent case, both are actually solutes. A and B both are solutes because both are actually in the two phases. But between this component A and B, I say either component A and B or species A and B. Okay, both are the same. So we will say that component A is more volatile than component B. Okay, so we will assume this so that the subsequent discussion can be followed by this particular assumption. Now, if you look at this a mixture of A and B and you say what is the phase equilibrium for a binary mixture, you will see that it is little bit more complicated than the pure phases. Okay, suppose if you consider pure A or pure B, you can actually nicely show the phase behavior in the pressure and temperature diagram. You will see a characteristic equilibrium line like this. You got triple point here, this is triple point, and you have got critical point here. So when I say critical point, there is a corresponding critical temperature and critical pressure. Okay, so this will be liquid, this is vapor, and this is solid. This is for pure A. You can do a similar plot for pure B also. Okay, so if you look at the pure A or pure B case, there is a line which is called the vapor liquid equilibrium line. If I take any point in this line, you will see that it will phase separate into liquid and a vapor. However, the liquid and vapor both will be pure components. They are not mixtures. Okay, they are pure component. A will be liquid will be pure A, and the vapor will also be pure A. So you need only two variables here to show the phase behavior. All the phases can be mapped here. Depending upon the choice of the temperature and pressure, it can be either in a solid phase, or it can be liquid phase, or it can be a vapor, or it can be critical state, or it can be a coexisting phases of liquid and vapor, liquid and solid, and so on. Okay, so this is something you are all aware of. But when I look at A and B together and I say under what condition they will be in single phase like liquid, or a single phase like gas, or when they will be together as a vapor liquid mixture. Okay, so in this case we will see that PTXY. So this is a PTXY diagram is a VLE data of a binary mixture of a two component system. This is something you must have studied in chemical engineering thermodynamics. So let's briefly go through this details. So the PTXY diagram looks something like this. So here for the pure component case, we saw that all the phases can be mapped into a P and T, pressure and temperature variables. When you have a binary mixture of A and B, you have to worry about temperature, pressure, but also the composition. Okay, for a liquid phase, I need to know what is the composition, temperature, and pressure. Similarly for the vapor phase also. So now the degrees of freedom for each phase becomes 3 instead of 2. Okay, so here this is pressure and this is temperature, and the third axis here is chosen as the composition axis. So here X means composition of more volatile species, in this case A. Okay, mole fraction of A in the liquid, and Y is the mole fraction of A in the vapor. Just X and Y is enough in this case because it's a binary mixture. If I know X, I know the composition of B, 1 minus X. Similarly, Y and 1 minus Y. So knowing the composition of one of the component, mole fraction of one of the component also sets the composition of the other component. Okay, so here X and Y are the mole fraction of A in the liquid and in the gas. So since X and Y both vary from 0 to 1, and that's what we are taking as the another axis here. So pressure goes up in this particular axis, temperature goes in this axis, and the composition start from X equal to 0 here and X equal to 1, or Y equal to 0 to Y equal to 1. Okay, so it's a little bit complicated plot because it's a 3-dimensional. Okay, so if I look at this particular line where X equal to 1 or Y equal to 1, that is basically pure component A. Okay, so I'm looking at the surface, the wall corresponding to this particular edge, and you see this line, that is going here, this particular line I am highlighting, this is the vapor pressure of A going from all the way to the triple point to the critical point. This is the vapor pressure line for pure component A, okay, across phases. Similarly, if you look at this particular point where x and y are 0, that corresponds to pure component B, okay, and then if you look at that particular surface on the other side, and that would be this line representing the vapor pressure line for the pure B, again going from its own triple point to the critical point. And then in between, if you take any particular composition, then we are talking about binary mixture. In that binary mixture, then you basically have this two surface loops, okay, that shows coexistence between both liquid and gas phase, okay. So understanding this is a little bit difficult, so what we are going to do is we are going to cut this surface either at a constant temperature or at a constant pressure. So this particular cut that I see here is cut at particular constant pressure, okay. Then you will see this kind of a loop going from, extending all the way from vapor pressure of B to vapor pressure of the other way around. So if I cut at constant pressure, this will change from two boiling points, TB to TA, whereas if I cut with respect to constant temperature, and you will see again this kind of loop structure which extends from pure vapor pressure A to pure vapor pressure B, okay, and anything in between. So now let's look at this cross sections. So first we will talk about constant pressure phase diagram. When I say constant pressure phase diagram, what I mean is I take this particular plot and decide a particular pressure and then do a horizontal cut here, okay. So this particular cut here is at a constant pressure. So we cut along the constant pressure and then look at what the projection is, and you will see that should give us something like this figure. So this figure that you see here is actually cut by a constant pressure line. When you do that, you see the pressure is held constant. You can make different cuts though, okay. So here we have taken one particular pressure and cut it, and then you will see that there is a temperature on the y-axis and the composition on the x-axis, okay. When you keep the pressure constant, temperature and compositions become variables here. So first of all, when you look at this, is at x-axis here we have x and y, that's a composition. So this corresponds to pure A, and this point corresponds to pure B, okay. And then if you look at pure A, this particular point is the boiling temperature of pure A for this particular pressure. As you know, if you change the pressure, the boiling point also changes, right? But here we have held the pressure constant. For this particular pressure, this point here corresponds to the boiling temperature, boiling point of pure component A. Whereas when you look at x and y equal to 0, then we are talking about pure component B, and this temperature will be the boiling point of species B, okay. So therefore the range of temperature in this plot will go from TA to TB, okay, boiling point of A to boiling point of B, okay. However, if you take any component in the middle between 0 and 1, you see that the temperature of boiling will be between T and TB, okay. It will be in the range of TA to TB. Now to kind of understand what's really happening here, and another thing I should mention also is that there is a two curve here. The top curve is called the dew point curve, which is basically y versus t, and the bottom curve is known as the bubble point curve, which is basically x versus t, okay. So anything below this bubble point will be a pure liquid. It's a binary component, but they will exist as a pure liquid. If you go above the top curve, it will exist as a vapor, two component but still vapor. So again, pressure is held constant. Now I can change different temperature and different composition, and I can see what is the state of the matter here. Any composition below the line, below the bubble point line, will be all liquid. Any component above the top curve, which is called the dew point curve, would be a vapor of two component system for this particular pressure. Now, if I take any point within this loop, within these two curves, for example, if I take point E, I can create a composition corresponding to this particular temperature. You see, this temperature lies between T and TB. Between two temperature T and TB, I can choose particular temperature and I choose particular composition corresponding to this point E. And you will see this will not be a stable mixture, it will immediately phase separate into two phases, liquid phase and the gas phase or vapor phase. And it will phase separate such a way that the vapor will have a composition corresponding to point F and the liquid composition corresponding to point D. Okay. Again, any composition below the bubble point will be a pure liquid, any point above the dew point curve would be a pure vapor. But if you create any composition within these two loops or within these two lines, it will phase separate into liquid and vapor which are in equilibrium. That's why we call this as a vapor liquid equilibrium curves. Any point taken at E, composition E, based on this temperature and this composition, average composition can be this, but then it will phase separate into liquid and gas phase. And the composition of the components in both phases will be different. Okay. So, the vapor phase will have a composition corresponding to F and the liquid phase will have a composition corresponding to D. We only said that if I make a composition at F, it will phase separate into two phases, gas and liquid, but we can also find out how much moles will be the liquid and how much moles will be the gas. We can also calculate that by doing a simple mass balance. So, let us say that we start with E moles of A plus B binary mixture with a composition Z. Okay, this is something you can experimentally prepare. You decide a temperature, you decide the composition corresponding to Z, and that will be your point E. Now, once you let it equilibrate, it will phase separate into two phases, and the both phases will have different moles and different compositions. Okay, let's see that you have D moles of liquid with composition XD or X. Okay, so that would be just here. This is the composition of the liquid, and let us say F is the moles of vapor with composition Y. So, that is this. Remember, both X and Y are read in the X axis here. X axis is for both X and Y. Now, you can write a total balance that total moles will be that D plus F should be equal to E, and then you can also do a species balance that D times X plus F times Y should be equal to E times Z. Okay, X, Y, Z, these are all compositions in the liquid, vapor and in the mixture. Now, I can replace E with D plus F times Z. So, I have two equations here. So, I am trying to replace this E with respect to D plus F. Then I can replace, I can write the ratio of D by F. So, what is the ratio of D by F? It says the number of moles of liquid over number of moles of the vapor, that ratio. Mole ratios of the liquid and the vapor should be equal to Y minus Z by Z minus X. So, what is Y minus Z? Here, Y minus Z is nothing but the line, the length of the line between F and E. Okay, so this is line FE. And what is Z minus X? So Z is here, X is here, so ED, line ED. Okay, so based on the location of a E with respect to DF line, you can find the mole ratio, right? Based on simple mole balance here. Suppose if I make, let's say if I make a point here, let's say I create a composition somewhere here corresponding to E prime. This will also phase separate into liquid and vapor, and those will also have the same composition like the one before. Composition remain the same because they all lie in the same tie line, but the relative amounts of vapor and liquid will be different because I've changed the line proportions of E prime F versus D E prime. Okay, so any composition you take on this line, tie line, will exactly give you the same composition of the liquid and vapor. However, the relative amounts of vapor and liquid will be different, and that you can obtain based on this lever rule or simple mass balance here. Okay, so for point E prime, you will see that D by F will be equal to line F E prime by line E prime D. So what would happen? Are you getting more liquid or less liquid? By going from E to E prime, will you get more liquid or more vapor? Again, please check again. This D by F is given by this line length F E prime over D E prime. What has happened to this ratio? Has it increased or decreased? Decreased. So what that means? D has decreased, right? So D is what? D is liquid. Okay, so that is decreased and more vapor would have formed. Okay, so this relationship is useful in determining which is more and which is less. Okay, now another important thing to see is that we will also look at what happens when we start with point G, which is well into the pure liquid form, and then we slowly heat it and see what are the changes that will happen to the mixture. So let's say you start with point G and then you heat it. When you heat it, simply this composition remains the same, and then once you reach the temperature corresponding to H, this is where you hit the VLE, vapor liquid equilibrium. Until then it's pure liquid. Okay, so basically it gets superheated, the liquid gets superheated. At some point of time here, you will see that the first bubble, the first vapor will form. Okay, the first vapor is basically a bubble, and the bubble will have a composition corresponding to point G. When you bring the system to H, the first vapor bubble forms, and that vapor will have a composition corresponding to J. Okay, now let's say you have closed this vessel and you continue to heat this further. When you heat this further, you may go here somewhere. Okay, but that is within the two-phase region. Okay, and it's going to phase separate into vapor and liquid, and the liquid will have a composition corresponding to here, and the vapor corresponding to composition here. Between this point and this point, the average composition remains the same because you've closed the vessel, the total mass has to be inside the vessel. So the average composition remains the same. However, it has become more like a two-phase now. One that is liquid phase corresponding to this composition, and this corresponding to the vapor phase. If you continue the heating further, let's say you go to point this. At this point, it will phase separate into two phases, L and K, and the liquid composition corresponds to L, and the vapor composition corresponding to K. And again continue further, you reach point M. By this point M, you might have vaporized almost all the liquid. At point M, the last drop of liquid is evaporating or vaporizing, and the last drop of liquid will have a composition N, and subsequently it's a vapor, superheated vapor, all the way up to O. So we start with the liquid and we end with the pure vapor, but in between the temperature corresponding to TH and TM, in that range of temperature TH and TM, you have a range of temperature within which the two-phase regions are observed. and depending upon how you move, the composition of the both phases are keep changing. So by changing this temperature of the system, you are changing the composition of both phases also. Okay, is that clear? And this is also reason why we call this as a bubble point curve and dew point curve, that at point H I said the first bubble is formed corresponding to the composition J. So that's why we say this is the first bubble forming point. So bubble point curves. So the envelope of many bubble point curves, bubble points give you the bubble point curve. Similarly, the last point at M is the last droplet that is evaporating. Okay, so and that we call as a dew point. In other words, suppose if you come from the top, let's say you start with superheated vapor and you cool it. Okay, so from O to M, this is a simple cooling with no phase change, only vapor is present and just get cooled. The moment you come to point M, the first liquid will form, that's called a dew, and that dew will have a composition of N, and then you continue further, whatever I said about G to O, the reverse will happen. Now, while this pressure constant Txy, this is called Txy diagram, because Txy, these are all shown here as a variable here. Another useful way of representing this diagram is what is called this xy diagram. In Txy diagram, we have three variables. In xy, we have only two variables, x and y. The way we construct this xy diagram is, we go to the tie line in the two-phase mixture, and then I find the equilibrium composition x and y, and I point it here. For example, this point P corresponds to xd and yf. Okay, and this corresponds to a particular temperature. So this point temperature says that vapor and liquid are in equilibrium corresponding to liquid composition x at D and vapor composition y at F, and I can collect yf and xd. This is yf, this is xd, that is one point P. Similarly, I can collect point H and J, so that would be somewhere here. This is yj and this is xh, and then collect this point N and M, so that can be somewhere here. This is ym, this is xn. So collection of tie line points plotted x versus y is the xy diagram. Okay, and this is the equilibrium line that we will be using for our mass transfer operation of distillation. This is what we call as a equilibrium line. Sorry, repeat xy meaning? Okay, so what I am saying is, you understand what Txy diagram is? So Txy diagram is obtained by taking this constant pressure line, and then you get this two-phase equilibrium line. So here I can draw many tie lines within this two-phase, not vertically, so horizontal lines. You see, each of these lines are horizontal lines, right? I can choose a range of temperature, and all that will give me a tie line. Each corresponding temperature will give me a tie line, and I look at the composition at the bubble curve and the dew point curve. Those are the pair of xy values. Those xy value I can plot it here. So here I have y, here I have x. This is called xy diagram or the equilibrium diagram. So here I have assumed that A is more volatile. That means compared to the liquid phase composition, the gas phase composition will be more for A. That's why this line is above the 45-degree line. If I consider point along this 45-degree line, x and y are equal. The liquid composition and vapor composition will be same along the 45-degree line. But the equilibrium line actually lies above that, which means y is always more than x. That can happen only if A is more volatile than B. If I do the same thing for component B, that will lie below the 45-degree line, because for the B, x is more than y. Now I was telling about more volatile, A is more volatile than B, but we also can define a quantity that says how much A is volatile than B. Okay, so we are going to introduce a term called a relative volatility to quantify to what extent A is more volatile than B. To quantify the relative volatility, we define a parameter alpha as something like this. So, this relative volatility alpha is defined as the ratios of the concentration ratio of the components in one phase over the other. Okay, what I mean by that? So, I am looking at one ratio here, y by 1 minus y. So, y is the composition of the component A in the gas phase, 1 minus y is the composition of component B in the gas phase. So, y by 1 minus y is the ratios of the concentration of A to B in the gas. In the x axis also I have x by 1 minus x, which basically is nothing but the ratio of the composite ratio of the mole fraction of A to B in the liquid phase. Now I am taking the ratio of these two ratios. Okay, I first find the composition ratio of A to B in the gas phase and then the liquid phase, and I take the ratio of these two gas to liquid ratios. Now this alpha basically tells you how much is my equilibrium line is away from the 45-degree line. If alpha is very small, it means it's actually very close to the 45-degree line. If alpha is more, I am departing further away from the 45-degree line. Okay, let's say if I have y equal to x, that is the composition in both gas phase and liquid phase are same. If x and y are same, you will see that alpha is actually equal to 1. Okay, that means there is no, the relative volatility is 1 means that there is no preference of one component over the other in distribution, in its distribution in the gas and liquid phase. Okay, both are equally distributed. So that would actually correspond to the line 45-degree line I have shown here. This line here corresponds to alpha equal to 1. For any real system where one component is more volatile than the other, you will see alpha greater than 1. If you make alpha larger than 1, it's better. Okay, because for every partial evaporation you are enriching gas more than the liquid easily. Okay, but if you have a choice, is there any way, since the component A and B, the chemical mixtures are known, how do we actually change this relative volatility? Because it looks like everything is fixed, right? The component A and B are fixed, its vapor pressures are fixed, so there's not much you can do about relative volatility, isn't it? Or not? I'll come back to this later and I'll tell you that you can change the working pressure. The total pressure, if you change, you can correspondingly change the relative volatility to some extent. Okay, if not completely. We'll talk about that later. Now, so far I've been talking about a TXY diagram where pressure was held constant. Another way is to go back to this entire three-dimensional phase diagram. So instead of looking at constant pressure, you can also look at constant temperature. So along the constant temperature line, you take a cut and then you see what the projection is, and that basically gives us what is called this PXY diagram. Note that here the temperature is constant. In the PTXY diagram, we are keeping the temperature constant. At a constant temperature, we have made a cut, and that projection will give you a PXY diagram where pressure is now variable as well as the compositions. So here x and y equal to 0 basically means pure B, x and y equal to 1 basically means pure A. So when you have pure A, this phase equilibrium line terminates at vapor pressure of A. This vapor pressure of A corresponds to the temperature that you have held fixed constant. If you change the temperature at which you cut this, the vapor pressure also will change. Similarly, for pure B, this will be the vapor pressure of B. So between these two vapor pressure A and B, you will see that the composition can change. For example, you can start with this point. So remember here, temperature is held constant, pressure is varied. Okay, so pressure is also a knob by which you can control the phase equilibria. In the case of temperature, TXY diagram, the pressure was held constant and we started with the liquid and then we heated slowly to go to the vapor phase, two phase and then fully vapor phase. In the case of constant temperature case, the pressure has to be manipulated. Okay, so here you will see the liquid is stable at high pressure and vapor is stable at low pressure. It's the opposite of the TXY diagram. In the TXY diagram, liquid was stable at low temperature and vapor was stable at high temperature. So here the liquid is stable at high pressure, okay, and vapor is stable at low pressure. This again follows from thermodynamics. So let's say you start with the point W, which corresponds to a binary liquid mixture, pure liquid, no vapor here. So here what you do, you decrease the pressure, you depressurize the system, keeping the temperature constant. So it's an isothermal operation. Okay, keeping temperature constant, you can slowly decrease the pressure. When you decrease the pressure, you come to point U. Okay, at point U, the first bubble will form, and that bubble will have a composition corresponding to this point. And if you continue to decrease the pressure, you come somewhere here. Again, the system will phase separate into liquid and vapor. The liquid composition corresponding to this point, vapor corresponding to this point, and then if you continue further, you come to this line TV, tie line. So here again, the liquid will have a composition corresponding to T, vapor corresponding to V. All along, you see the composition has to come vertically here, because the average composition has to remain the same. When you come to point S, that's when the last liquid droplet will vaporize, and the last liquid droplet will have a composition corresponding to the point here, and then subsequently from S to R you are completely into a vapor phase. Okay, so here you can see the dew point curve lies below and the bubble point curves lie above. Usually the students get confused between the bubble point, dew point when you go from TXY diagram to PXY diagram. Okay, the easiest thing to remember here is, intuitively you can expect whether at high temperature liquid is stable or vapor is stable. Similarly, in terms of pressure, liquid is stable or vapor is stable. So if you know this concept, you can identify easily whether the bubble point will be above or below for a given diagram. So like I said before, in this case also you can plot XY diagram. So you have a 45-degree line here and then Y versus X, and these Y versus X plot can be taken from the tie lines here. Like I said before, the way we constructed XY diagram from the TXY diagram, the same way from PXY diagram also you can get the XY diagram. Okay, so you read out these points XY and then you map into this. Okay, so you'll have a XY diagram. It has to mention whether P is constant or T is constant. In this case, T is constant. Whereas in the previous case, here P is constant. So these discussions should have happened in chemical engineering thermodynamics course. You must have calculated this VLE data. So do you recollect these discussions? No, VLE data. But end of the calculation, you should be plotting XY diagram like this. No. What about this this two phase equilibrium? This was discussed. No. No, this kind of phase diagram and walking through this phase transitions as you heat or cool, or if you depressurize, and those discussion did not happen. Okay, so if this is not covered, I urge you to go through the textbook. It's very nicely explained. Okay, read through the first few pages of distillation introduction section. These are very beautifully discussed. Okay, so just brush it up, because this is very, very important and crucial to understand what's happening. When we deal with distillation, we talk about gas, liquid, composition changing, and the design. All that will depend on how much you understand the graphical nature of these plots. many times the calculations are done graphically in distillation, okay, in compared to absorption where it was semi-analytical. Some are analytical, some are graphical, some are numerical. But when it comes to distillation, it is very few cases, very ideal cases we can do analytical, but rest of them are graphical or numerical. So it's very important to understand what is the meaning of XY diagram, what is the meaning of TXY diagram, where is the bubble point curve, where is the dew point curve, what's the tie line, and how do I understand the relative proportions of liquid and vapor. So all this is very critical, and I can only build on what you already know from your thermodynamics course. So if it's not covered in thermodynamics course, I request you kind of go through and read this through. Okay, if you have any questions, you can come back. I will assume that you will do this, and then I'll build on from these equilibrium data. Okay, I did not spend much time here because I thought it's been done, but I leave it to you to read this. And again, if you have any question, you can always come back. This is very important. Okay, so how we understand equilibrium data is very important before, because I'm going to bring in operating line to this, and I'm going to bring in Q line to this. So like in absorption case, we had three things, right? Equilibrium line, operating line, driving force line, and then we manipulated to get the design. In the same way in distillation, we got the equilibrium line, operating line will come from material balance, and then instead of a driving force line, we will have something called a feed line. Okay, so again, the design will involve manipulation of these three concepts. Okay, so as I said before, things will get only more and more complicated. So you have to follow this course. So last time reading will not help. Every day you have to read. Okay, so things won't be easy. Okay, so yeah, okay, we'll stop here.